Alright, we're back for yet another video. Today, in true work from home style, I am going to be recording in my underwear. Unfortunately, you guys don't get a sneak peek yet, but perhaps as an incentive for you all to subscribe, I'll do some dirty underwear shots at 1,000. But okay, actually though, let's talk about the video for today, which is going to be chain replication. Fun fact, the guy who actually wrote this paper was my operating systems professor, which is pretty sweet. But yeah, let's talk about his work. Okay, chain replication. So what is it? Unlike some of the other replication schemes that we've spoken about, in 2004 the original paper for chain replication came out and basically said here's a way that we're going to achieve both strong consistency and high availability while maintaining pretty high throughput. Then there's kind of the subsequent paper that came out called CRAQ, C-R-A-Q, and basically that even provides more read throughput. So I'm going to go through how all of these processes work. So for starters, let's talk about chain replication writes. Imagine we have this kind of chain of database nodes, right? So we have a head, two replicas, and a tail. And then we have a client. And what the client does is it goes and first writes to the head of the list. The head is then going to propagate those writes such that the head passes to the first replica passes to the second replica passes to the tail, which is the last node in that list. Once the tail receives the write, it's going to go ahead and acknowledge that message and pass it back through the chain. So as you can see, now we have a chain of acknowledgements going back through those replicas. Once the head receives the acknowledgement for that write, it's going to go back to the client and say, good job, the write was successful. It's propagated through the chain. Okay. In terms of reads, all reads are actually going to be made from the tail. And so this is kind of the unique part of chain replication that ensures strong consistency. Remember that the second a client hears that its write is successful or committed, it means that that write is actually in the tail. So by reading from the tail, we can see only up-to-date data. Okay, so let's talk about failover, because I mentioned that this schema was particularly high availability. Well, why is that? Generally speaking, we're not using something like a gossip protocol here because that has all sorts of potential issues where, if two links can't communicate with each other, one might think that the other's down and the other might think that, the first is down, and then the chain becomes completely babbled. So what you do is you use an external coordination service like Zookeeper, which we've discussed in the past, that uses some sort of consensus algorithm to determine which nodes are running and which nodes are not running. So anyways, here's what happens in certain failure scenarios. If a head fails, then you go ahead and just promote the head's next node to the head, because that's going to have pretty much all the writes that the head had. It may have some uncommitted ones, but it's not a big deal if uncommitted writes are lost because the client never received an acknowledge message for that. If the tail has failed, then we're going to go ahead and start executing reads from the replica right before the tail. So that works well because, again, that should have all the writes that the tail had because it's quite literally giving them to the tail, so we're not losing any data. And then if any middle node has failed, basically we would do the same thing that we might do in terms of removing a node from a linked list, and we would just go ahead and have to kind of remove it from the chain and take each adjacent replica and make sure that the chain is put back together, and then pass the writes from the left replica to the right one and make sure everything is updated. Okay, in terms of the analysis of chain replication and how it's good and how it's not so great, it's really strong, or amazing, that there is strong consistency and linearizability in this type of replication schema. We have a total ordering of writes. Everything is eventually going to be reaching the tail in some specified order, which is great. Additionally, writes are going to be less expensive than single leader replication. This is because even though every single write goes to the head, and kind of in the same sense, every single write goes to the leader in single leader replication, the leader in single leader replication is sending all of those writes to every single replica. Whereas in chain replication, there's only one write being sent from the head at a time. So, those operations are actually less expensive. We're less likely to overload the head node. And then also, if we're looking at Raft or Paxos, kind of the same deal happens where you have that leader and it's sending out a bunch of network calls at the same time. The biggest con is obviously the read throughput's limited to just one node. I put unless sharded here on the slide, and that's because, if we have multiple chains for each partition, so, one chain per partition, then you can actually increase read throughput. But even still, you can't just say, oh, we have the same type of data being served from, these two chains. That doesn't work. Basically, if you want to serve some data, you're limited to one chain for it, and as a result, you're limited to the read throughput of just the tail node. And then additionally, it's very easy to have bottlenecks, meaning that one slow node in the chain is going to slow down the entire process of writes, because writes have to go through every single replica. Okay, now let's talk about crack. So crack is kind of a modification to chain replication that allows you to achieve much higher read throughput by taking reads from any of the replicas. So how can we actually do that? Well, let's imagine first that we have this kind of chain replication setup right here, and then it's going to start in a consistent state. So everything that you see right here, every replica, has the key Jordan and the value sexy. And right now, see, look at 1 and clean. 1 is known as the version number, and clean I'll describe in a second. So let's imagine now that I perform a write. Now instead of Jordan being sexy, he's hot. So the head is going to take this write, and it's going to increment the version number. And it's going to put the parameter dirty next to it. Dirty basically means that the write has yet to be acknowledged. So it hasn't received the acknowledgement back from the next replica. Hence, this is considered a dirty write, and we'll see what that kind of means for the future. Okay, so now we're going to go ahead and propagate that right through, and all the replicas are going to have dirty as their state for, version number 2, until the write eventually reaches the tail node. The tail node can't have any dirty writes because it's supposed to be the source of truth. So it goes and overwrites the clean key, which was sexy, and now has version 2 for hot. It's going to start sending back acknowledgments now, and as the acknowledgments go through every single replica, they're going to say, okay, now I can finally label hot as clean, and as a result, since this key is now clean, or the key value pair is clean, I can go ahead and get rid of the older versions of that. So now replica 3 is going to say hot 2 clean, replica 2 has hot 2 clean, replica 1 has hot 2 clean. Okay, great. So that all makes sense, but how do we actually do reads? How does this increase read throughput? Well, there are basically two possible scenarios. So imagine we're trying to read a key, and that's going to go to a replica where the highest version number available of the key is clean. And basically, so as you can see, since we're in a consistent state here, hot 2 clean is the same amongst all replicas. So it means that, say the read went to this second replica here, it's guaranteed that it's going to return hot. And we know that that's the state that the tail has because it's labeled as clean. However, what if I went and made the write thick and it got to the second replica and then we tried to read from the second replica? Well, something now is going to happen. The second replica is going to say, oh shoot, now I realize that thick is actually a dirty write, and as a result of that, I have to reach out to the tail to see what the greatest value of the current clean write is in order to go ahead and return that. So it's going to go ahead and contact the tail node, and what's going to happen is the tail node says, oh, actually, the highest version I currently have says that the value is hot. So replica is going to say, okay, I'm just going to return hot. Now you might say to yourself here, oh, well, just looking at this, why can't we just return the clean write? Well, we can't return the clean write because it's possible that thick did actually get written on tail. However, the acknowledgement just hasn't been sent back to the replica yet. And as a result of that, then we would return hot too, and that thinking that was the right value, when in reality the tail had already processed the right thick. So ultimately, it is important that we actually end up reaching out to the tail to get the proper version number. Okay, so in terms of the evaluation of crack or the analysis, in read-heavy workloads, this is actually going to be super useful. The majority of the reads are going to be clean, and as a result, the read throughput should scale almost linearly to the number of replicas. If there are a ton of writes, well, we're going to have a lot more dirty reads and eventually have to contact the tail node much more. That being said, we would have been contacting the tail node every single time anyway, and this still does take some load off the tail node, because instead of sending back a potentially super large file over the network to the client, the tail node just sends a version number back to another replica, which it's probably closer in proximity to, and the version number is going to be smaller than potentially a large file. So even though crack still does suffer from the same problems as chain replication in terms of one node potentially acting as a bottleneck, using this allows for pretty high read throughputs in a chain replication scheme, as well as still the ability to maintain strong consistency. Okay, so in conclusion, it's pretty cool that we've finally discovered like a high availability, strongly consistent replication schema that can achieve relatively, high throughput. That being said, it isn't used a ton in practice, but there are some systems that use it. I think Amazon still ends up using it in something called Aurora. But even though it's probably not the most useful thing to know about chain replication in something like a systems design interview, I think that it might very much impress your interviewer if you're able to kind of bring up chain replication as an option, if you ever might need strong consistency. Obviously, one way to do strong consistency is to deal with, something like a consensus algorithm, like Paxos or Raft, and then, just use sync commands in order to achieve strong consistency, or putting your reads in the log. However, again, that really overloads that one leader node, and in comparison, chain replication kind of spreads out that load. And so it's interesting to kind of have that discussion. Anyways, guys, I know this video was kind of short. I hope it was useful though, and I think I'm going to start talking about object storage and CDNs in the next